Okay, everybody, thanks for joining. It is my pleasure today to substitute for Adam and introduce you all to today's speaker, which is Adam. So Adam is going to talk about the interpretation of quantum mechanics, and he told me that the talk is going to be a little bit more relaxed. So I encourage everybody to ask questions during the talk, grab a coffee and have a piece of cake if you would like. With that out of the way, Adam, take it away.
Thank you for the kind introduction. And as Peter said, cake seminars are already kind of informal, but this will be a little bit more informal than usual. I'm not going to talk about my own research or even really a topic I'm an expert, just something I'm an interested amateur in that I like to read about in my spare time. This case
historically, I think this is the first ever non-theory center cake seminar. So this is it's the first, I think, at the lab.
Oh, really?
It's a CNF center.
Well, it's a cake seminar, so it's kind of, I only sent it to the theory center mailing list.
Oh, so it's not a CNF. Okay.
No, it's not.
Okay, my bad. Ignore me. All right.
Well, that's just my affiliation since I'm employed by the CNF. So this seminar came about because we had a theory center seminar a few months ago given by Jacob Berendis on his new interpretation of quantum mechanics that it was different than the usual topic for our theory center seminars, but it was really interesting. And a few people, especially Christian, expressed interest in hearing more about the topic, and Christian actually suggested I should give a cake seminar about interpretation. So I went with the suggestion, and this talk is what resulted from it. Although I'm not an expert in it, I hope that I'll be able to teach you all something interesting and get you all a bit interested in the topic. So the starting point, of course, is quantum mechanics, something that we and basically every other physicist alive is an expert in. It's the most successful theory of science that's ever been constructed, and it has a few simple mathematical axioms. We describe physical systems in terms of Hilbert spaces. We ascribe to a physical system a state that's, at least in the pure case, given by a vector or array in the Hilbert space. A composite system has a Hilbert space given by the tensor product of the Hilbert spaces of the individual systems. In addition, we ascribe to physical observables of the system self-adjoint operators acting on the Hilbert space. The possible measurement outcomes for this observable are given by the spectrum of the operator, eigenvalues in the case that the spectrum is discrete, and the expectation value in the probability theory sense is given by that operator sandwich between the vector and its dual in the Hilbert space. Now, if you actually measure this observable and you get an eigenvalue or something in the spectrum, then you spontaneously must replace the state with the eigenstate associated with that eigenvalue, because you now know what the value of that observable is. Of course, the state has to be the eigenstate. This is sometimes known as the collapse postulate or the reduction postulate. The peculiarity here that will be the running theme throughout this talk and is kind of the running theme in the field of interpretations is that these axioms very heavily emphasize measurement. Your self-adjoint operator corresponds to an observable. The eigenvalues are possible measurement outcomes. You talk about expectation values upon measurement, and the collapse rule applies when you measure the system. The reason that this is peculiar is because when you have a classical theory, measurement is not a distinct process. You don't have a separate measurement axiom. A measurement is just another physical process you use to infer something about the system with the help of the dynamical laws of the theory. For instance, if you want to measure the magnitude and position of a star or a comet or a planet using a telescope, well, the way that the light moves is described by geometric optics or wave optics. The way that it goes through your scope, the way that it travels through lenses and bounces off mirrors, in fact, even the way that it enters your eye and impinges on the retina is described by the same theories that describe the behavior of the object you're trying to measure. There's no distinct set of rules for measurement, device, and system. It's all just one big theory of physics. The same applies to a voltmeter. The operations of the voltmeter are described by the same laws of electrodynamics as the thing you're trying to measure the voltage of. Likewise, for barometers and thermometers, they're described by continuum mechanics and thermodynamics, just the same as the things you're trying to measure properties of. Quantum mechanics seems to be a bit different in that regard, at least in the original interpretation, Copenhagen interpretation. The Copenhagen interpretation is a big set of, it has a lot of philosophical baggage attached to it, but one of the central tenets of it, especially as emphasized by Niels Bohr, is that classical concepts in classical physics are necessary in the description of quantum phenomena. So according to the writings of Bohr and Heisenberg, it is necessary when you are describing an experiment to study a quantum mechanical system to perform a theoretical cut called the Heisenberg cut much of the time between the quantum system, which is described by your laws of quantum mechanics. It's given by a state in Hilbert space that evolves unitarily by the Schrödinger equation, versus a classical measuring device, which you describe in terms of classical concepts, that is classical configuration. It evolves according to Hamilton's equations. And there's no way, according to them, to have one theory to describe everything. This is very different than the case you have in classical physics, and it also presents some conceptual problems. Now, before getting into these conceptual problems, I do want to emphasize the Copenhagen interpretation is a very rich set of views besides just the necessity of classical concepts. But all of the other things, besides the necessity of dividing the world into quantum and classical, are partly philosophical views, partly actually inevitable consequences of quantum theory. I won't dwell on this too much now because I'll get to them later when I talk about other interpretations. But what is called the measurement problem, the fundamental ambiguity of what you mean by measurement, and the problem that you have to have two completely different theories of physics to describe a measurement of a quantum system. This is an actual scientific problem. The axioms of quantum mechanics don't tell you what a measurement is. It doesn't tell you when a measurement occurs, where this divide between classical and quantum is supposed to be. And it doesn't really clarify why incommensurable theories are needed to describe a measurement. Now, the lack, kind of a cartoonish representation of it, the lack of clarity about where to place the Heisenberg cut can be illustrated as follows. Imagine Peter the cat here is an experimentalist who wants to study the properties of some microscopic system. Say he wants to measure the projection of the spin of an atom along a particular axis. He might use some sort of measuring device represented by the lamb chop toy here, but imagine the lamb chop toy is a Gerlach apparatus or something. You would theoretically introduce a cut between the microscopic system, which you describe using quantum mechanics. It has a wave function that exists in Hilbert space and evolves according to the Schrödinger equation as it passes through the inhomogeneous magnetic field. Then the apparatus itself is described classically. The inhomogeneous magnetic field is described classically. But your measurement device is made of atoms. It's a physical system. And atoms obey the laws of quantum mechanics. And from the tensor product axiom, they should have a Hilbert space, which is just the tensor product of the Hilbert spaces of all the atoms that make it up. So it should evolve according to quantum mechanics. So why not move the cut back between Peter the cat, the experimentalist, and the device he's using to measure the properties of the atom? Now you describe the device as a quantum system that evolves according to Schrödinger's equation. But the ambiguity does not end there. And this was very strongly emphasized by von Neumann back in the 1930s. You could go another step back. Peter the cat is a physical system made of atoms and should have a Hilbert space. You can ascribe a state in Hilbert space to them that evolves unitarily according to quantum mechanics. So maybe you need to place the cut further back, treat Peter as just another quantum system, and then you have another outside system, Wendy the cat, who is classical and describes Peter in terms of a wave function. Where does this stop? According to the Copenhagen interpretation, you have to stop somewhere because classical concepts are necessary in order to make sense of quantum mechanics to begin with, so you need a cut. But anywhere you could place the cut on the classical side is really just another physical system that should obey the laws of quantum mechanics. So there seems to be this sort of vagueness in the Copenhagen interpretation. So this vagueness, this lack of clarity of what measurement is, when it occurs, why you need two different theories to describe the measurement process, is kind of the outstanding problem that different interpretations of quantum mechanics intend to address. It's the main reason that the Copenhagen interpretation isn't universally accepted by everyone, and there are dozens of proliferating alternatives that are floating around. Because there are so many, there's no way I can go over all of them in an hour, and I'm going to focus on just 3 classes of proposed solutions, and in fact, one representative example from each. One of these is hidden variables theories, in which the classical-like description in terms of configurations is always valid even for microscopic systems. Then I will talk about the relative state interpretation, which goes in the opposite direction. It says the Hilbert space description from the axioms of quantum mechanics is always valid even for macroscopic systems. And lastly, I'll look at the set of interpretations that is actually most popular among folks specializing in quantum information, quantum computing, and so on now, informational interpretations, with QBism as a representative example. Their way of getting around the Heisenberg cut is to strategically avoid saying anything about objective states of affairs and say that the Hilbert space probability calculus is just a subjective probability calculus done by subjective agents. Unfortunately, I'm going to leave many examples out, like spontaneous collapse theories and theories about backwards causation. But these are kind of the 3 most popular classes.
So, Adam, just one question. What you said about the measurement problem applies equally to quantum field theory or this matrix theory and the idea of asymptotic states. So even there we need a classical system to measure the.
I mean,
that come out.
With
this is never emphasized.
Oh yeah, it's not really emphasized, but yeah, with S matrix theory, you are projecting onto some final state. I mean, you're taking the matrix element initial state S matrix, like the unitary evolution matrix final state. So there's an implicit assumption you're doing some sort of measurement that projects out onto some basis that you can measure with what final states you're choosing to get matrix elements of.
Well, that depends on your choice of final state, right? You can imagine the asymptotic of the final state is your classical quantity you can see.
Yeah.
And all you can do, imagine you have a detector at the Fermi scale all the way down, that you are more sensitive to the quantum effect.
Right.
The measurement itself is a part of your system.
Yeah.
So basically, the detector or the calorimeters are collapsing the wave function at the end of. Yeah, right.
Whenever you do a measurement, in the sense you collapse the quantum system to the classical configuration at that time.
Yeah, and the fundamental ambiguity, of course, is, well, why should the calorimeter be treated as a classical system when it's really made of atoms that obey mechanical laws? For all practical purposes, of course, we know from experience and from a lot of other things like decoherence, which I'll go into later in the talk, that for practical purposes, we don't need to worry about the measurement problem, which is why most physicists don't care that much about interpretation. For all practical purposes, the Copenhagen interpretation is fine. It's just, if you want to think of it as a fundamental theory that describes the entire universe and not just a tool for doing practical calculations in our own field, that's where you run into the problem. But before I get into the interpretations themselves, I want to emphasize that this is a really messy field with no consensus. Even the most popular interpretation, which is the traditional Copenhagen interpretation, according to a recent survey done by Elizabeth Gibney at Nature, has less than 50% support among working physicists. It's 36%. And then most of them are not even confident in it being the right interpretation. And you kind of see this as a trend for all of the other interpretations. The information-based approaches, many worlds, which I'm calling the relative state here, pilot wave theory, very unpopular in comparison. But even within each camp, the people who are confident in it are a small portion. So this is not a topic in which we have a consensus view or certainty. It's a very messy topic, and that's something that you should bear in mind going in.
I'll give you another example. In addition to quantum mechanics, the heavy ion experiment for,
Oh, with the initial state fluctuations.
and the question is whether or not the medium when you produce can be part of your system or part of your separate medium, because people talk about probe.
Yeah,
Then you have a jet come out, then whether jet formation itself says to by the medium or jet can be treated as the probe. Where is the cut? Where's the separation?
yeah, exactly. So actually, yeah, things like the initial state fluctuations in heavy ion collisions could be an interesting example of where this question actually does start becoming practical.
Right. Because the initial fluctuation determine what your medium is.
Right. That's a good point. Thanks for bringing it up. All right. And before getting into what is controversial, I really want to emphasize that the reason the interpretation issue doesn't affect everyday physics is because most things about quantum mechanics aren't controversial. Everyone accepts quantum mechanics is true, aside from maybe a very small percentage of people. All the popular interpretations are ways of trying to add clarity to quantum mechanics, especially regarding the measurement process. They're not attempts to replace or overthrow quantum mechanics. Second of all, the operator algebra itself isn't debated. Most of what we actually do when we're doing quantum mechanics involves calculating possible states the system can have, possible eigenvalues, commutation relations, things like that. Nobody debates that because all of that is just mathematically clear. And one other thing that is kind of interesting to note, if you read a lot of the interpretations literature, determinism versus randomness isn't real important. There are some interpretations that are deterministic, but determinism isn't the reason that the advocates of these interpretations latch onto them. You'd think that it would be important from popular science media or from reading internet arguments on social media about quantum mechanics, especially when people start trying to bring free will into it. But the technical literature is mainly concerned with the measurement problem, and that's the main motivation behind all of the disagreements. So with that, I want to get into the first class, which is hidden variables theories. Ooh, hopefully I don't go too far off the time. So before I say what exactly, well, I'll kind of say what they are while saying why. The main reason why people consider hidden variables is that they want to give a consistent account of quantum mechanics as a self-contained theory at all times, even during the measurement process, so that you don't have this Heisenberg cut whose location is uncertain. The idea behind hidden variables, this might be a bit of a simplification, especially when newer ones like Berendis's interpretation comes up. But the idea behind hidden variables is that your Hilbert space description is always valid for both microscopic and macroscopic systems, and the configuration space description is always valid for microscopic and macroscopic configurations. So you have a wave function, but you also have your system is always in a definite configuration. Your wave function always evolves by Schrodinger's equation, and the configuration evolves according to something like the Hamilton equations with some sort of quantum modification. What hidden variable theories are not are competing theories to quantum mechanics. I got a referee report for one of my papers where I used pilot wave theory that I thought made a really nice metaphor. They described what I was doing as calculating mechanical properties of the hydrogen atom with de Broglie Bohm theory as decoration. And I think that's a really nice way of putting it. The substance of quantum mechanics is fixed. The hidden variables theories are like icing that you add on top of a cake. They're not the main thing, and they're not meant to replace the cake, just to add to it. So they're not really a way of trying to recover classical physics, and they're not even necessarily a way of trying to save determinism from quantum randomness. In fact, most hidden variables theories are stochastic. The example hidden variables theory I'll go into is the pilot wave interpretation. It's also known as de Broglie-Bohm theory and as Bohmian mechanics. The idea behind it is that in addition to having a wave function that describes your total system, there's a wave function, in fact, of the entire universe according to this. All of your particles have exact positions at all times, and they follow continuous trajectories through space. The wave function then guides the particle trajectories. A very nice illustration of why it's called pilot wave is because the wave function, say in this double slit example, goes through both slits, follows all possible paths according to Huygens principle or the path integral formulation, and creates an interference pattern. Every instance of this, you have one particle that moves through a definite trajectory, but it's not a classical trajectory. The trajectory is guided by the interference pattern created by the wave. So if you have a large ensemble of particles, one after the other, then they'll build up an interference pattern, not because each particle is interfering with itself, but because the pilot wave is interfering with itself and the particle follows trajectories informed by that.
So,
Yeah.
the concept of trajectories here is like in the functional integral, or I'm a bit.
I'll clarify that the next slide.
Robert, there's also clarification needed, relationship between particle and wave, right?
So there is both the particle and the wave. So there's a wave function, which obeys Schrodinger's equation. You do a polar decomposition of the wave function. You write it as a real valued modulus function times e to the power of I times a phase function. You can write Schrodinger's equation then as two coupled equations for the modulus and phase. The modulus function obeys something that looks like a continuity equation, suggestive of probability flow, although that doesn't formally prove that the modulus is probability, it's just suggestive, with a velocity given by the gradient of the phase function divided by m. And then the phase function obeys something that looks just like the Hamilton-Jacobi equation, this new additional potential. So the idea here is that you have some configuration variable. The initial configuration is unknown. It's kind of like a free variable. But the velocity of this configuration is determined by the gradient of the phase of the wave function. So pilot wave theory simply postulates that in addition to the stuff that you can actually measure, there is an exact particle position whose velocity is determined by the wave function. So there is a particle and there is a wave at the same time. Hence it's adding decoration to quantum mechanics in a sense.
I'm a bit lost. I mean, in the Feynman path integral, consider the transition amplitude from one, say, space-time point to another space-time point.
Yeah.
Imagine that come about as a sum of all possible trajectories, and each one of
Yeah,
those.
these are not the same trajectories.
So the trajectories you have here are not.
No, they're not the ones in the Feynman path integral.
Can you then what's the object you consider here, a wave function, or?
So there's a wave function.
I mean, is this a way of rewriting the wave function, or is this like can we express this as some kind of like transition amplitude from some given configuration at some time to another given configuration at another time, and then tell a story how this transition comes about? Or?
So I think that you're speaking a different language than this interpretation tries to speak. You have a wave function at all times. The wave function obeys all the usual rules of quantum mechanics. The transition amplitudes tell you things like the probability amplitude, conditional probability amplitude, so they're related just to the wave function. The particle positions are something kind of outside of the quantum mechanical formalism by itself. They're kind of a new ingredient that's added in. It's just that you kind of imagine an ensemble of possible particle trajectories that are that basically follow the probability flow.
At the first level, this is really just like Schrödinger quantum mechanics, where you have the wave function as a function of the generalized coordinates and time, and it is prepared in whatever way, and we know how the equation describes how it evolves in time, and you're just rewriting the wave function and its time evolution in a certain way that lends itself to particular interpretation.
Yeah.
Okay.
Yep, that's all.
Okay.
And of course, these equations are just they're largely mathematically equivalent to standard quantum mechanics. Although technically, because of continuity of there's a quantization condition on the phase that is not expressed just by writing these equations. And so technically this still has more continuities too.
This might be a stupid question, but why does this help us with the measurement problem? I mean, this doesn't really.
It's what I'll get into in the next few slides. I guess the short answer is that in principle, anything that you actually observe on a macroscopic scale can be stated in terms of configurations. And if you assume that everything described by quantum mechanics has a definite configuration at all times, it's just that you don't know what it is before the interaction, then you're just, well, observing something that was there already. I'll clarify a little bit. So this is actually kind of an attempt to segue into the clarification. One of the peculiarities here, if you take this modified Hamilton-Jacobi equation seriously, and you take this continuity equation as a kind of a flow of possible trajectories seriously, then it would seem that the gradient of the phase evaluated at wherever the particle actually is should be its momentum. However, this Bohmian momentum, as it's called, is not equal to the canonical momentum that you would actually measure in an experiment. And actually, I probably should have mentioned on the slide this as an example. Whenever you have a real valued wave function or a wave function whose phase is constant, like the ground state of the hydrogen atom, this two-sided derivative will be 0, or the phase is constant, so the gradient of the phase is going to be 0. So in something like the ground state of the hydrogen atom, according to the pilot wave interpretation, the electron is just sitting there a fixed distance from the proton, never moving. But of course, that's not what you would actually measure if you were to measure the momentum of the electron. It would always be non-zero. It would obey the Heisenberg uncertainty principle. So the canonical momentum and the Bohmian momentum, as it's called, are different objects in general, with the sole exception of if you have a momentum eigenstate, so a plane wave, then this two-sided derivative will give you the canonical momentum. And this is kind of an interesting thing because when you do a momentum measurement, it effectively creates the momentum you measure rather than revealing a momentum that was there previously. So how do you do a measurement? In pilot wave theory, measurement is just another physical process. You have some sort of interaction Hamiltonian that creates a correlation between the canonical momentum of your microscopic system and some macroscopic configuration. You set something up so that if the particle goes through with one momentum, the pointer turns a certain amount. If it's going faster, the pointer turns more. Maybe you use deflections with magnetic fields or something like that to help measure the momentum. But the idea here is that you just have an interaction Hamiltonian and you apply unitary evolution to the joint system as the particle goes through the apparatus. They're both described quantum mechanically, but according to pilot wave theory, they both have a definite configuration at all times. After the system has evolved, the Bohmian momentum is still the gradient of the phase function, but it's the phase function of the total system, because when you've entangled systems together, only the joint system has a wave function. So the Bohmian momentum depends on this phase function, which depends both on the microscopic position of the particle and the macroscopic configuration. So the macroscopic configuration determines the Bohmian momentum. So that's a really weird thing. And there are kind of two lessons here. Measurement is just another physical process. You create this correlation between configuration of a macroscopic system and whatever microscopic observable you want to measure. And because configurations exist at all times, you can just look at the device. Its configuration doesn't collapse, it just was that already. Hence why you don't need a collapse axiom. And second of all, the measured momentum is not, in fact, measurement probably isn't a good word. You didn't figure out what momentum the system had before you measured it. You caused it to have that momentum by the interaction. That's seems like a very peculiar aspect of pilot wave theory, but it turns out to reflect a structural property of quantum mechanics that appears in all of the interpretations, and that is contextuality.
Just to understand if I'm honest, the only thing I understand from the last slide is your statement that the measurement process doesn't collapse the wave function, it creates the wave function.
It doesn't create the wave function. The wave function just unitarily evolves all the time.
I'll say not creates the wave function, but it kind of changed. Is this a way to explain the change in the wave function due to the measurement in some continuous way as some,
So I definitely explained it very poorly, I guess. The wave function just evolves by Schrodinger's equation the entire time. Yeah. And it kind of now contains say different branches or channels in all of the possible measurement outcomes. So if you have something where the momentum can be 1, 2, 3, 4, all of these. So
you have a set of variables that describe the measurement outcomes. Yeah?
So the wave function will then evolve into different channels where the momentum is 1 in particular units, and the configuration has a pointer pointing to the number 1. And the wave function also has a support in the part of the configuration space of the joint system where the momentum is 2 and the pointer is pointing at 2. So the wave function contains all these possibilities, but in addition to there being the wave function, there's an actual configuration of your system, and the actual configuration just lives in one of these branches. And the actual configuration evolves continuously at all times with the velocity of, or the generalized velocity with respect to the generalized coordinates being given by the wave function. So there's a definite state at all times, and there's a wave function at all times. And these empty branches of the wave function also continue evolving at all times, but no longer have any effect on the system.
So it's like the wave function has an additional variable that describes in some sense, the state of the measuring device or the outcome of the measurement, like 1 or 2. And then in principle, if you didn't do a measurement, it could propagate as a superposition in this, or it would have components both with 1 and 2. So if you make a measurement, then only one of these components will continue to evolve. Is that?
So in this interpretation, the wave function continues to have branches over all the possibilities. But there's always a definite configuration of everything at all times. The particles making up, say, your pointer are always somewhere at all times, and they only follow one of the branches of the wave function. All of the other branches of the wave function continue to exist and continue to evolve, but they are so far apart in the configuration space that they no longer influence the system.
Maybe this can be presented slightly differently, I guess. When you have a system, you have wave function and on a certain given space, then they can evolve
Yeah.
whatever happened before any measurement. Suppose you are the outsider try to think or measure that system, you have no control, it's by itself. But once you impose measurement in the sense of introducing interaction to that system, and if you want to have put an instrument there,
Yeah.
say for example, a system made up of all the charged particles, they interact with some among themselves. Then suppose I put the magnetic field around it,
Right.
and the particle with certain momentum will have different trajectory.
Right.
Yeah. So by doing so, in a sense, already add external, in a sense, I imposed an interaction with that system. The new system is no longer the same system. It's a system. The old system plus me as
Yeah.
all the equipment I put in.
They become entangled, so wave function only exists for the joint system.
That's right. So your eventual system should take care of themselves, develop a new wave function
Yes.
for the whole system.
Right.
So
So perhaps a way to think about it is if you had something, if you put something near one of the slits to measure which slit it went through, it would of course destroy the interference pattern. And the way that it destroys the interference pattern in pilot wave theory is that once you put something that the particle going through the slit can interact with, you no longer have a wave function of just the particle going through. You only have a joint wave function of the particle going through and the probe.
Yeah.
So you enlarge your configuration space. So you imagine that the configuration space has something going this way if it goes through one slit, something going into the screen if it goes through the other slit. So the trajectories on this side now go through the configuration space this way, trajectories through this slit go through the configuration space this way. And they're moving away from each other in configuration space, so they no longer interfere.
that's how it becomes classical, the measure or effectively.
Yeah, it becomes classical because the interference stops happening. But there's always a actual trajectory at all times, and there's always a wave function at all times. And there's no sharp break between the classical and the quantum behavior. The configuration and the wave function are always there, but it's when you create these really complicated correlations that you end up getting effectively classical behavior because the interference stops happening. It's really hard to get your head around because it occurs in configuration space and not physical space.
And then, okay, now. Okay, it seems that the key concept here is like separation of trajectory in a different.
Yes,
In
absolutely.
a new variable, so that you separate them into classes.
Yes, exactly.
And then they can no longer interfere, so
Yep.
that, they're still like quantum mechanical, et cetera, but the trajectories in different classes are so far apart that they effectively don't interfere.
Exactly. I should have put it in those words. That was very eloquently put. Right. So the peculiar thing here is that before you actually did the measurement in this example, the canonical momentum that your device was registering didn't exist. It basically came about because of the measurement. The interaction caused the particle to follow a trajectory in which it had that momentum. And this sort of thing is actually a fairly generic feature of quantum mechanics and interpretations of it. And it's actually very much in line with a lot of the things that Niels Bohr wrote. That Niels Bohr would say things along the lines of the microscopic properties of your quantum system only had meaning with respect to an experimental context or an experimental setup. And this is somewhat codified by a particular mathematical theorem, usually attributed to Kochen and Specker, but actually proved by Bell around a year before. That hidden variables theories of quantum mechanics need to be contextual. Formally, if you have a Hilbert space with 3 or more dimensions, the theorem mathematically says that you can't find a commuting algebra that simultaneously includes all commuting subalgebras in the Hilbert space. But at the level of the measurement problem, what's used for interpretation is that measurements do not generically reveal properties that were there before the measurement. And quantum non-locality, which is something a lot of people make a big deal about, is a corollary of this, because the properties that you're concerned about the things that you want to measure might be space-like separated. And you can only really assign values to the things you're measuring if you fully specify the experimental context. Pilot wave theory is contextual and non-local, as the theorem requires. The guidance equation, that the Bohmian momentum that tells you how your trajectories go, depends on the phase function for the wave function of the entire system. And if it's entangled with something, that means it depends on the configuration of spatially distant things. So that's kind of peculiar, but there's a really nice example of contextuality that a bunch of people came up with. It's called the GHZ experiment after Greenberger, Horn, and Zellinger. Shimony and Merman were very instrumental in developing this picture, but unfortunately their names didn't get into the acronym. But you consider an entangled state of 3 particles, or 3 qubits, basically, 2 state systems. I'm imagining them as spin up and down states for spin half particles, but that can't be taken too literally because obviously this doesn't obey Fermi statistics. But you have a state that looks like this, all up plus all down. And it's pretty easy to confirm that it's eigenstates of all of these operators. Spin x on each of the 3 particles, well, the sigma x operator just swaps up and down, so these 2 things get swapped. Eigenvalue +1. If you use 2 y's and an x, well, the sigma y operator swaps them, but multiplies by I if you started with up, multiplies by minus I if you started with down. So if you have 2 sigma y's, you get I squared, or minus I squared, you get a minus overall. So this is an eigenstate of all these operators, which are, well, they're tensor products of spins of different particles. So these, of course, commute within themselves. These are well-defined operators. If you assume that the system has pre-existing values for each of these sigma x's and sigma y's before measurement, so each one of these is +1 or -1 before the measurement, and you assume that's true for all possible combinations, and that it doesn't depend on how you set your detectors are just going to register something that's there already. Well, each of these can be +1 or -1, and you might notice that the sigma x for each particle and the sigma y for each particle appears twice. So assume these have numerical values of +1 or -1, multiply these together, +1, +1, +1, and you derive that +1 has to equal -1, which of course is not true. So the assumption that it's possible to assign numerical values to all of these spin projections simultaneously in a way that's independent of how you've chosen to set up your detectors is false. So something like this GHZ setup cannot reveal properties that were there before measurement. And in fact, in pilot wave theory and other hidden variables theories, spin is not a property of the particle.
Just one question. Okay, you have a product space.
Yes.
the operators you write down here are direct products, so
Yes.
that's tensor
products.
products. You still call that a spin measurement? I mean, you're not adding the angular momenta of the individual
No.
qubits here.
So the idea here is that you prepare a joint system in this state, and then you send each particle away to a different detector. And then each detector can choose to measure either the X projection of the spin or the Y projection of the spin of the particle that it received.
You prepare this state in the center, in the center, and then you send the same state away in three directions, and each one measures
the spin of one of the three particles.
one of the three particles, and then the statement is what?
The statement is that if you assume that the X and Y spin projections of each of the three particles has some pre-existing value before you do the measurement, and the measurement is just revealing that value, then you cannot reproduce the predictions of quantum mechanics.
This seems to me to involve something beyond the example you just said. You said you prepare this state.
Yes.
You send it out to be measured independently in its 1, 2, 3 spin projection. What do we get from that? What's the statement about that?
So the first of these particles in this list, it can be up or down, and of course, whether it's up or down along the z-axis depends on what the other particles are. So the person at detector A, say it's Alice, can choose to measure either the X projection of the spin, sigma X operator, self-adjoint observable. She can find +1 or -1, or she can choose to measure the Y projection of the spin, get +1 or -1. So the assumption beyond quantum mechanics that will turn out to contradict quantum mechanics is that there is some X projection of the spin before she measured it, and the measurement just reveals what it was before she measured it. And if she changes the detector to measure Y instead, it reveals something that existed before she measured it, and she didn't change what it was beforehand by choosing to set her detector.
That's like some philosophical statement, but how do you see that? How is that negated by the outcome of the measurement?
Okay, so the statement is that you cannot make that assumption and reproduce what quantum mechanics would reproduce. And the reason is, say, you assume that the sigma X measurement by Alice, the sigma XA here, has some pre-existing value, +1 or -1. You don't know what it is, but it's one of those. So it's just a number. And the sigma Y is also a number, +1 or -1. So if you take sigma X times sigma Y times sigma X times sigma Y, that's +1 squared or -1 squared. You just get 1 by multiplying those numbers together. Same thing for B, say Bob is there, and C, say Charlie is there. So you also have to assume, because quantum mechanics is true, that whatever this pre-existing value for the X projection is that Alice and Bob and Charlie would measure, they have to multiply out to give you +1. And if two of them chose to measure Y instead of X, say Alice and Bob choose to measure Y while Charlie measures X, the values they get have to multiply out to -1 because this state is an eigenvalue of this operator. So if you assume that all of these correspond to numbers that are being revealed, then you could just multiply all 4 of these together as if they're numbers, ignoring the fact that they really don't commute because they're operators, but we're assuming that they stand in for numbers that are being just revealed by measurement.
So I would say these days the workflow is that you prepare the state, put it in the center, send it out to the three measuring devices.
Of the three particles to each of them.
Yes, then they measure, they choose to measure, each one chooses to measure either X or either Y.
Yes,
And then they get together and multiply their numbers.
yes,
And check these conditions here.
yes.
That's,
And because quantum mechanics is true, they would always find one of these conditions to be
and,
satisfied.
okay. And in the putative hidden variable, or in the other interpretation, this would not be required, or what's,
So-
where's the
So
paradox now, or where's
okay,
the?
this counterfactual, this not true hidden variable theory, in which the things they're measuring exist before they measure them. So there is an X projection before Alice measures it. It's +1 or -1, and she doesn't know what it will be, but it was already there. And it was there regardless of whether she was choosing to measure it or not. And that's also true for the Y. So there are numbers corresponding to these operators.
Are you saying that if this hidden variable interpretation were true, they could measure a different thing, or?
If this hidden variable theory were true, then it would not be able to reproduce all four of these conditions. Because there would need to be a number corresponding to each of these that would give you +1 equals -1. So basically, the argument is that there is no such hidden variable theory in which spin measurements reveal something that was already there.
So the statement is you could not, you would not get this necessary outcome with hidden variable theory.
With a specific kind of hidden variable theory, a non-contextual.
The problem is that the hidden variable theory is typically posed to make the spooky action at a distance go away. And you're saying that the only way that your hidden variable theory as posed here could work is if there still is spooky action at a distance.
There has to be the spooky action at a distance. That's the only way a hidden variables theory could reproduce.
Yeah.
So pilot wave theory, for example, does have the spooky action at a distance. So pilot wave theory is able to reproduce these predictions, but it's because the spin projection doesn't correspond to something that was there before the measurement. And moreover, the way that you set the detector can influence what happens at the other detectors, even if all of these events occur at space-like separation.
Adam, looking at your slide counts and simultaneously at the watch.
I didn't anticipate that the discussion would take me this far behind.
So what I'm proposing is maybe we could just have your speaker next week as well, and then we could sort of get the full talk. Or we wrap up somehow short.
How about we wrap up hidden variables and then state next
Finish
time?
this topic, I mean, it's.
So I want to also make the point that this idea of contextuality, that the thing you're observing depends on the total experimental setup and is not there outside of the measurement, is not actually that peculiar. Things like that happen in real life. Color perception, I think, is a really nice example of it. And I want to point to my wife's engagement ring. It's made of a material called alexandrite, which has a very peculiar color changing property. It has a very asymmetric crystal lattice that also polarizes light. So the color that it appears can depend on the lighting conditions, including the light's polarization. So in sunlight, it often appears greenish, and in incandescent light, it looks purple. Moreover, a lot of humans, a fairly large portion, I think close to 13% of men, have red-green color blindness. So not only do the lighting conditions, but also the details of color vision of the eyes of the person influence a lot what color you perceive. So you need a specification of the entire experimental context in order to know what color you're going to see. And the color doesn't actually exist when nobody's looking at it. We might conventionally say something like, oh, the top of this desk is a light brown. We say is, even though the light brown isn't there when no one's looking. Because this is something that's stable enough that anyone who looks at it will say that it's light bound. And that could be the case for a lot of quantum observables. If you have the eigenstate of some operator, we could conventionally say that it has that particular energy or it has that particular spin projection, but strictly speaking, that only might have meaning in the context of the experimental set. Now, before, I guess, ending this first seminar in this now becoming a seminar series, I want to highlight some problems with pilot wave theory. Why do only 7% of physicists say that it is their preferred interpretation? Well, it has some problems, that's why. One of the big ones, and this was actually Wolfgang Pauli's one of his reasons for rejecting pilot wave theory when de Broglie told him about it in the 1920s, is that it breaks the symmetry of quantum mechanics. Quantum mechanics treats all self-adjoint operators and all bases equally. But pilot wave theory tells you that, oh, it's the configuration, the position observables that tell you about what's really there, and all of the other observables are created by the measurement context. You could equally well devise a hidden variable theory in which the momentum operator tells you about what's really there and everything else emerges. And you could make it consistent with all of the statistical predictions of quantum mechanics. So why should you assume that, one proposed completion of quantum mechanics with extra entities is right and the other isn't? There'd be no way to empirically distinguish. The breaking of symmetry seems kind of arbitrary. Another issue has to do with what people in the pilot wave community call the quantum equilibrium hypothesis. There's no a priori reason that the squared modulus of the wave function should give a probability density in this interpretation. If you assume that at some initial time, your probability is given by the squared modulus of the wave function, then the continuity equation guarantees that it will give the probability distribution at all other times. But you happen to have these trajectories that are guided by the wave function according to, well, this equation. You also happen to have this equation, but why should the R squared be interpreted as a probability? That's not a priori clear in this interpretation. And the last one, which is kind of the main reason that I'm not really satisfied with pilot wave theory, even though I kind of otherwise like it, is that it doesn't play well with relativity. There are relativistic formulations that have been attempted, but they all have various sorts of pathologies and peculiarities. Perhaps the most damning of them is that the most well-developed relativistic formulations all require a preferred foliation of space-time be added to the axioms of the theory, which even if you could find the statistical predictions to be Lorentz covariant, you're then saying that nature isn't fundamentally Lorentz covariant, which I think is in violation of the spirit of special relativity. So I guess another example of breaking an empirical symmetry in the axioms of the theory. And recently there's been this really nice preprint by Jacob Berendis about problems with pilot wave theory that I think is one of the better articles written criticizing the interpretation. So I'd recommend checking that out. There are other hidden variables theories. We had a very nice seminar by Jacob Berendis a few months ago on his indivisible stochastic dynamics. There's another stochastic theory from half a century ago by Nelson, which isn't really as elegant as Berendis's interpretation. So if you're going to check out one stochastic interpretation, I would recommend checking out Berendis's. And there's also something that is not very popular, but seems to be gaining a bit of traction. 1% of physicists apparently prefer it, superdeterminism, but it's kind of a contrived theory, and I think I won't get into it. But that's what I have to say about hidden variables, and I guess next time I'll talk about the relative state interpretation.
All right, thank you. Do we have any questions that haven't been asked already?
Lots of questions. I don't know where to start.
Well, you have time until next week.
Yeah, let's, thanks for this.
You can check if we have
That's
questions.
all for your time and patience.
It would be nice if one would have one like practical problem where this really hits you. So I mean, if this is like all about interpretation, then it's kind of like optional or in a difference. Is there some real like real life problem where you get say qualitatively different conclusions that have some consequence depending on whether you adopt one or the other interpretation?
I don't think so, because all of these interpretations are designed to give exactly the same empirical predictions as standard quantum mechanics. There are some of the less popular interpretations do in principle give different predictions, like the spontaneous collapse theories will tell you that there is a scale in which things become classical. And then you can test that because you could look for apparent nonlinearities of Schrodinger's equation or violations of the Born rule. And so far, no deviations from the Born rule have been found. I do think that, so although these all make the same predictions, I think that there is a benefit to thinking about them because they can spur on different ways of thinking about quantum mechanics, and that can lead to new discoveries. So
I mean, it's very interesting. I'm just like, I just mean to like to focus the discussion that you have of real life problem with different outcomes, and you say depending on whether we adopt method A or method B, we get different outcomes, and
I don't think that that will happen with any of the popular interpretations, but I think that what has happened multiple times is that people thinking about these problems and trying to come up with ways of validating them ultimately have come up with new technologies. Like quantum computing was proposed in the context of people thinking about the many worlds interpretation. The existence of quantum computers does not prove the many worlds interpretation, but it was spurred on by thinking about it. A lot of these communications protocols, quantum teleportation, and all of that were devised either by people working on pilot wave theory or by people working in informational interpretations of quantum mechanics. So they spur on ways of thinking that can help you make discoveries, but ultimately they are just all different ways of thinking of quantum mechanics.
I have yet to see a real life consequence coming out of quantum computing.
Okay, that's fair. Maybe quantum computing, not so much, but the secure communications protocols are probably going to be very consequential in the future. And I'm sure they're the real reason that so much money is being poured into quantum technology.
Any questions on that?
No, I didn't see, but we can ask.
Okay, I think then we can close for today. Thanks to Adam.
Thank you.
And I believe there's still cake left, so if you still want to.
Wait, sorry, can I ask a quick question?
Really issues how and how you and also
Oh,